As we've been learning about redox reactions, you will see that in every reaction, there is an atom that undergoes oxidation and there is an atom that undergoes reduction. The oxidation and the reduction in a reaction can be split apart, and those are called half reactions. And that's what this sheet here is looking at. It's looking at what are the electrons doing in the oxidation part of the reaction and what are they doing in the reduction part of the reaction. So remember that in oxidation, the atom that is being oxidized is losing electrons, and the atom that is being reduced is gaining electrons. Some other terms to know would be oxidizing agent and reducing agent. The oxidizing agent takes electrons from something else, thus oxidizing the other thing. In this case, the oxidizing agent would be the wolf, and it undergoes reduction. Because it oxidizes something else, it has to take electrons and it's being reduced. The reducing agent is the opposite of that. It provides electrons, and thus it is reducing the other atom. And that makes it the goat and undergoing oxidation. Every reaction needs to have an oxidizing agent and a reducing agent in order to be a redox reaction. So let's examine what we see on our half reaction sheet. On the left side, we have all of the oxidation half reactions. And in the reaction, we can see what are the reactants. So in this first one, the reactant would be fluoride ion, and the products would be fluorine gas and 2 electrons. These electrons go somewhere. The reason this is an oxidation half reaction is because the electrons exist on the product side, thus implying that the electrons initially were with the reactants and now they are somewhere with the products. And where they go is to whatever is being reduced. So we have the reducing agent, the thing that is losing electrons, and the electrode potential. I'm not going to say much about the electrode potential, except for this. When the electrode potential is negative, this is an unfavorable reaction, and the more positive it is, the more favorable the reaction is. So down here at the bottom, we have lithium, lithium solid turning into lithium aqueous and giving away its electron. This is a highly favorable reaction because the lithium ion is much more stable than the lithium solid. And so all of these reactions are showing some sort of energy profile like this. And when it's positive, it's going down, and when the electrode potential is negative, then it's going up. And the amount that comes after it tells you kind of how up or down that energy is changing. On the other side, we have the reduction half reactions, and it is the opposite of the oxidation reactions in that the electrons appear on the reactant side because the species is being reduced. Therefore, it is gaining electrons. The electrode potential plus and minus is the same, but you'll notice that these are exact opposites from one side to the other. And it should make sense to you that the electrode potentials are the same number, just a change in the sign, meaning that if the reaction for oxidation is very unfavorable, that must mean that the reaction for reduction is very favorable. We can see that here with our lithium, very unfavorable to become lithium solid would have to put energy in, and that would be going the opposite direction here. And we can conclude that that would be an unfavorable reaction denoted by the negative sign on the high voltage. It would take a lot of energy to turn lithium ion into lithium solid. Half reactions are handy because we can look at how the electrons are moving between one reaction versus the other, and every half reaction can be combined with another half reaction to make a fully balanced reaction. I'm going to write down the steps for combining half reactions, and then I'm going to show you an example. Here are the instructions. Please copy them down into your notes, and now I'm going to do an example. I'm going to do the combination of hydrogen sulfide and potassium permanganate. First thing I need to do is find those on my half sheet. So we're looking at HS2, here it is, and potassium permanganate. First step is to write them down with the arrows lined up. Next step is to add multipliers to make the electrons the same amount. So I have 2 electrons and 5 electrons, and I need those numbers to be the same. And so I'll multiply the top by 5 and the bottom by 2, and then I'll rewrite those underneath with the coefficients now based on the multiplier. Now I cancel the electrons, 10 and 10, and then I combine those into one reaction. You're combining the reactants onto one side and the products onto one side. And then I'm going to simplify by canceling out the H pluses on either side. So we're simplifying here. I have 10 over here. I'm going to cancel that out, and I'm going to make this one 6. Because if 10 are left over, then you only need 6 in the reaction. And there we go. That is your final reaction, and this is now balanced for the electrons. So instead of doing it like the wolves and goats, this is a simplified way where you use the half reactions.